Hello friends, welcome to engineering tutorial. Now in my previous videos I discussed about the various BJT configurations such as the common base, common emitter, common collector configuration, their operating principles and the various expressions for collector current and current amplification factor. Now in today's video we will discuss about a new concept associated with the operation of transistors or the BJTs. So we will discuss about load line, okay, load line analysis. So let's get started. So load line analysis. So what is load line in a BJT or a transistor? Now whenever we analyze the circuit of a transistor, it is generally required to determine the output current for various values of output voltage. Now normally the common emitter configuration of the BJT is used for amplification purpose. So the load line analysis always comes into play there. So generally it is required to determine the collector current, which is the output current for common emitter configuration, for various values of collector emitter voltage, which is the output voltage for common emitter configuration. So the method which is generally used to determine the collector current values for the various values of collector emitter voltage is called as the load line method. Okay, the method which is used is the load line. Now it is a very easy and precise method to determine this collector current values for various values of collector emitter voltage. So before we understand how to draw the load line, first let us see the circuit diagram for common emitter NPN BJT. Now the same circuit I have already discussed in the common emitter configuration. Here the NPN BJT is connected. Here the NPN BJT you can know because this arrowhead is pointing outwards from the base. Okay, so this signifies that it's the NPN BJT. Now this arrowhead, it points to the direction of flow of the emitter current, which is flowing outwards away from the BJT, while the collector and base currents are flowing towards or inwards to the BJT. Now this is the base emitter voltage, which is measured from the ground with respect to the base terminal, and this is the collector emitter voltage. Now this is the collector resistance, which is connected to the collector terminal. VBB and VCC are the biasing voltages which keep the emitter base junction forward biased and the collector base junction reverse biased under the normal active operations of the BJT. Now one thing to remember here is that, or to pay attention to, is that no signal, the input signal has not been applied. Okay, the input signal is not applied because for analysis of load line or to plot the load line, DC conditions are required. There should be no AC signal present. So this AC input or the signal which is to be amplified is absent, it's not applied. Okay, to maintain DC conditions in the circuit. Only under DC conditions the load line can be constructed. Okay. Now, so this is the circuit diagram for load line analysis, the common emitter BJT, NPN BJT configuration. Next, how the load line is to be drawn. First, if we apply Kirchhoff's voltage law or KVL in this collector emitter or output loop, we will get the following expression. Okay, the collector emitter voltage VCE is equal to VCC minus ICRC. Okay, this is the Kirchhoff's voltage law. VCC minus IC RC. This is the KVL equation if you apply Kirchhoff's voltage law here. Now, this expression is used to draw the load line. Now, here in this expression, VCC, which is the biasing voltage in the output loop, and the collector resistance, they have fixed values. Only variable elements are the collector emitter voltage or the output voltage VCE and the output current or the collector current IC. These two things are variable, these two things are fixed. VCC and RC are fixed, VCE and IC are variable. So, this can be represented in the form of a straight line equation, first degree equation, y equals to mx plus c. It can be converted into that form. How it can be done? By this, in this way. IC is equal to minus VCE by RC plus VCC by RC. We have just rewritten this equation in this form. Okay, how we have done that? We have taken this IC RC term towards the LHS. Okay, we took this towards the left and then we divided both the denominator on both sides by RC. Okay, we took ICRC here towards this side, then we divided RC in the denominator on both sides. So we got this expression, IC is equal to minus VCE by RC plus VCC by RC. Now you can pause the video here if you don't understand and just compare these two equations and follow how it has been done. We have taken IC RC towards the left, then we have divided RC in the denominator on both sides to get this expression. Now if we compare this expression with this straight line equation y equals to mx plus c, where y is the output or the generally y is the output, m is the slope, x is the input and c is the intercept. So if we compare this equation, this straight line equation with this, we'll get that y is equal to IC, x is equal to VCE, the slope is equal to minus 1 by RC, and the C constant value is VCC by RC. As VCC and RC are both constant values, so the ratio will also be a constant. Okay, so this is the straight line equation representation of the output KVL equation. Now, the next step is to plot the load line. Okay, now when we applied KVL in the output equation, we got this expression, VC is equal to VCC minus IC RC. Now put IC equals to 0 milliampere. What happens when IC is equal to 0 milliampere? When IC will be 0, the collector emitter voltage will be equal to VCC, which is the output biasing voltage, DC bias voltage. Now that VCC will be the maximum value of the collector emitter voltage. The maximum value which the collector emitter voltage can attain will be equal to VCC. So this is the first point of, or the one end of the end point of the load line which we desire to construct. Okay, VCE is equal to VCC is the first point of the load line. Remember that. When this is we obtain by substituting IC equals to 0 in the output KVL equation. So we get VCE is equal to VCC, which is the maximum value of VCE. Next, when we substitute VCE equals to 0 volt in the output KVL equation. Now let's say VCE we substitute here 0. So in that case, we will get ICRC equal to VCC and IC is equal to VCC by RC. Now this will be the maximum value which the collector current can attain. Okay, so the maximum value of collector current will be VCC by RC. Now this is the second end point of the load line. One end point was this VCC and the other end point is VCC by RC. So by joining these 2 points, okay, VCC and VCC by RC, these 2 points, the DC load line is constructed. Okay, so this is the DC load line. So here in the XY axis, the X axis is taken as VCE, the collector emitter voltage or the output voltage, and the y-axis is taken as the collector current or the output current for common emitter BJT configuration. Now, one of the endpoints which we found out was VCC. Okay, this endpoint VCC here marked by point B. This is one of the endpoint, and the other endpoint was VCC by RC. Here, VCC by RC. This is the maximum value of collector emitter voltage. This is the maximum value of collector current. This is the maximum value of collector emitter voltage. This is the maximum value of collector current. So when we join these 2 points, we get the DC load line. Okay, we get the DC load line. Next, why we require this DC load line? Okay, then comes the concept of operating point. Now you'll see that what is operating point, why is it required. Now in the beginning I said that here no AC signal is applied because we need DC conditions to draw the load line. Now the operating point is actually the zero signal values of collector current and collector emitter voltage. Now what is this zero signal values? Now this zero signal refers to the absence of input signal. Zero signal means no input AC signal has been applied to the BJT circuit. Okay, this condition, no input signal, means zero signal. Zero signal means no AC signal. Okay, understand this. Zero signal means no input AC signal, and those the values of collector current and collector emitter voltage in the absence of AC signal are called as operating point. Now it does not mean that each and every point on this load line is the operating point. It is not that. Okay, each and every point on this line AB is not the operating point. There are special points on this load line which can be designated as operating points. We will get to that soon. Now, so first have a look at this. Here if you see that this is the output characteristics of common emitter BJT configuration, which is a plot between the output voltage, which is the collector emitter voltage, and output current, which is the collector current, at constant values of input current, which is the base current. So at various values of base current IB, we plot the output characteristic curves. Now you see these points Q1, Q2, Q3. Now these are the intersection points between the load line and the output characteristic curves. Now it is this intersection points between the output characteristics and the load line which we call as the operating points. Okay, remember, the intersection point between the load line and the output characteristics is called as operating point. Okay, the point of intersection of the load line with the output characteristics of BJT is called as operating point. So here Q1, Q2, Q3 are the operating points for output plots at IB equals to 5 microampere, at IB equals to 10 microampere, and IB equals to 15 microampere. So if we select IB equals to 5 microampere, Q3 will be the operating point. If we select IB equals to 10 microampere, Q2 will be the operating point. And if we select IB equals to 15 microampere, Q1 will be the operating point. Okay, now these operating points are also called as quiescent point or silent point. It's also called as Q point. Now why this operating point is important? It is because when an input AC signal will be applied to the BJT, okay, when an input AC signal will be applied to the BJT, of course there will be variations in the collector current, isn't it? The collector current will change with respect to the input AC signal. At that time, the collector current will change or will vary around this operating point. Suppose we select Q1 as the operating point for IB equals to 15 microampere. The collector current will change around Q1. It will vary around Q1. If we select Q2 as the operating point, the collector current will change around Q2. If we select Q3 as the operating point, the collector current will change around Q3. So in order to get a reference point, we assign the operating points. We need to determine these operating points. That's why it is necessary. Now suppose we select IB equals to 5 microampere as the output characteristics, from where we have to define the operating point. Here the IB equals to 5 microampere, we have selected this plot, output plot. Now this load line intersects the output characteristics at Q. Now here the zero signal or Q point or quiescent values of collector emitter voltage and IC are VCE is equal to OC volts. Okay, OC. This is the Q point value for VCE, or the silent value or the zero signal value. Now for collector current, the zero signal value is OD. IC equals to OD milliampere, which is the zero signal value of collector current with respect to this point, Q point. This point as the Q point, which is the intersection of the output plot for IB equals to 5 microampere and the load line. So the load line is always plotted on the output characteristics curve of a BJT, and the point of intersection between the load line and the output characteristics is called as the operating point. Why the operating point is required? To get a reference point, because whenever an input AC signal will be applied, the collector current will change around that operating point. Okay, so here we have discussed about the load line analysis of a BJT, the KVL equation which is used to draw the load line, and then the concept of operating points. So how to the procedure to locate the operating points. So I hope you like this video. Please subscribe my channel Engineering Tutorial for more such videos related to electrical and electronics engineering. Have a great day. Thank you very much.